Hello student, to the Foundation of Classical Electrodynamics course. Under module 2, today we will going to discuss the dipole and quadrupole moment. Last year also we discussed, but today we will going to do some problem related to this. So, today we have class number 37 and we will going to discuss few problems related to quadrupole moment. So, before that let me remind what we have done. So, the definition wise the monopole moment is q is equal to integration of rho r prime dv prime. It is nothing but the total charge. Next, the dipole moment it is P defined by P, and by definition it is this quantity. And quadrupole moment which we define by q I j, this is a tensor component and we write it as half integration of 3 x I prime x j prime minus r prime square delta I j and then rho r prime dv prime. This is the way we defined the quadrupole moment. So, today let us discuss few problem. So, let me first write down the problem. So, it is say problem 1. So, I have a coordinate system like this. Suppose this is my x and this is my y, and we have 4 charge particle or 4 point charge are distributed like this. One is sitting here, another sitting is here. So, this charge is say plus q, this is minus q, this is plus q and this is minus q, where the separation from here to here, this is A, and here to here this is A. This is the geometry we have, and the problem is one, find out the dipole moment P. Second, find out the quadrupole moment. That means I need to find out all the components of q I j. Okay. And finally, find out the potential at r, some vector r, such that the mod of r is very greater than a. So, at long distance I want to find out the potential. So, this is the problem. So, I need to find out first the dipole moment, and then I find the quadrupole moment tensors, and then finally find out the potential. The standard problem, last year also we calculated a similar kind of problem, but we calculate only the dipole moment. Here we going to calculate the quadrupole moment as well. Well, so let me draw once again. So, the solution is like that. So, let me draw this once again. And this is my x axis, this is say y, and this is plus q, minus q, plus q, minus q. So, let us first, because in order to calculate the dipole moment or the quadrupole moment, I need to know the location, the position vector for all these point charges. So, that I first let us figure out. So, from here to here, so this is the position vector for the charge plus q, and let us say this position vector is chi 1. In a similar way, from here to here, this is the position vector, and say this is chi 2. Now, by symmetry I can say that, so the position vector of these two will be simply minus of chi 1 vector and minus of chi 2 vector. These are the position vectors. So, I can find out the position vector very easily, because I know what is the coordinates here. So, coordinates, since this is a, already mentioned that from here to here it is a, and from here to here this is a, they are forming a box like that. So, here the coordinate is a by 2, a by 2. The coordinate of this point is a by 2 minus of a by 2. Coordinate of this point is minus of a by 2, a by 2, and this is minus of a by 2, a by 2. These are the locations of these point charges. Once you know the location, then the next thing is very straightforward, and that is find out the chi 1. So, the chi 1 vector, which is the location of this, is simply a by 2 x unit vector plus y unit vector, and chi 2 is a by 2 x unit vector minus y unit vector. In a similar way, other two are negative of that vector. So, I am not writing that. For other 2 points you can find out, this is one is minus chi 1 and another is minus chi 2. Okay. So, next let us calculate directly the dipole moment. So, dipole moment of this system is, according to our rule, it is P, this is integration of r prime and then rho r prime dv prime. Now, rho is the density, and we know for discrete charge how the density is calculated. So, several times we are using this concept, a very important concept. So, let me write it. So, the rho for discrete charge is the density is qk delta r minus rk. This is the way we define the density, charge density of discrete charge. If there are n number of charges, I can write it in this way. So, I will going to exploit this expression here and write down r density of this system, charge density of the entire system, and that is q and then delta r prime minus the location of that minus q minus q delta the location of r prime. This one will be plus chi 2, because I am calculating this one, and then plus q delta r prime plus chi 1 and minus q delta r prime minus q 2. These are this is the density of the system, this discrete charge having this 4 discrete charge, whatever is whatever we are having here. So, these are the 4 discrete charges. So, one charge is sitting here, and for that it is chi 1, one charge is sitting here, for that it is minus chi 2. So, that is why I have a plus sign here. For this it is charge plus q, for that it is again minus chi 1, that is why I write plus chi 1 here in the delta function, and another is this one, for that it is chi 2 and I write minus chi 2. Okay. So, now simply this will be integration of r prime, and q is common, so I can take q outside, and we left with only the delta functions, and that is delta r prime minus this minus delta r prime plus this plus delta r prime plus this and minus delta r prime minus this over dv prime. Now, the delta function, once we have the delta function, then rest is very straightforward, because simply I just need to put. So, in this case I should put the value simply r prime. So, I just replace r prime to chi 1 vector. In this case I just replace minus of chi 2, in this case plus of minus of chi 1, and here minus of we have chi 2. So, minus of chi 2. So, here you can see that chi 1 and this chi1 will cancel out and plus chi2 and minus chi2 will cancel out. So, eventually what I am getting is 0. So, the dipole moment is 0 for this system. After doing all this calculation, we find that the dipole moment is 0, fine. Now, the next thing, that what should be the quadrupole moment for it. So, next we calculate the second part of this problem, that this is 2 and we want to calculate the quadrupole moment. Quadrupole moment, and that we define, definition is very important, you need to remember this definition, and it is 3 xi prime xj prime and then minus of delta ij r prime square and then rho r prime and dv prime. Now, I have already figured out the rho, and that will going to help me, because in this problem I need to put this rho value and rest of the thing is identical. So, let me write down the rho once again. The rho r prime for this system was simply taking q common, it was, I am writing the same thing multiple times, but anyway, then delta r prime plus chi2 vector and then plus, now q I take commons, I should not write q anymore. So, it should be simply delta r prime plus chi1 and then minus delta r prime minus chi2. This is my density. So, that density I will put here one by one. So, first let us calculate, because there should be 9 terms, q11, q12, q13 and then q221, q22, q23 and so on. But we know, so let me write down, we know that there are few properties that we discussed last day, and that is qij is qji, the tensor is symmetric, that is property number 1, and the property number 2 for this case is summation of qii is 0, it is a traceless, I can go to 1, 2, 3. So, if it is not that I need to record all the 9 components, but I can simply calculate few components and my total value, total tensor can be calculated. So, let us start with the calculation of q11. So, q11 is simply half of integration and then I have 3 x1 prime x1 prime minus r1, sorry, not r1, r prime square bracket closed, and then I have the entire delta function, and the entire delta function if I write, so it should be, okay, let me write it, it should be delta r prime minus chi 1 vector, then minus delta r prime plus chi 2 and then plus delta r prime plus chi 1 and minus delta r minus chi 2. How the chi 1 chi 2 is defined already I mentioned, and with a q term sitting here over multiplication over dv prime. Okay. So, now we have only the delta function and then here we have the function, but in this function here I am having x only the x component, because according to our notation x 1 is x, x 2 is y and x 3 is z. So, only the x component of the chi 1, chi 2, chi 1, chi 2 this x component will put, and in place of r prime square I just put whatever we have in the argument, that is chi 1 mod square. So, this simply gives me, if I start putting the value, because now I am dealing with the delta function, then it is, let us take q by 2 outside, because q is constant, so I can take it outside, and then I execute the integral. So, the first case I write 3, and for this case this is chi 1 and I know what is chi 1. What is chi 1? It is a 1 1 a 2 x and y. So, x component and y component are having a by 2. So, x component important, it is a by 2. So, I simply, so better I write it here, it will be helpful. So, somewhere, so my chi 1 vector is a by 2 x unit vector plus a by 2 y unit vector, and chi 2 vector is a by 2 x unit vector minus a by 2 y unit vector. So, here I am going to put this value, only the chi 1 a value. So, in place of x prime I just have a by 2, in place of x 1 again I have a by 2, and in place of r I should simply have the mod square of these things. So, what is the chi 1 mod square? It is simply a square by 4 plus a square by 4. So, it is a square divided by 2, that is the value. So, that value is simply a square divided by 2. My first, this I execute. Okay. Next I need to execute the next one. So, that is minus of 3, and now this is minus chi 2. So, minus chi 2 means I need to put the minus value of a 2, but I multiplied twice. So, it should be minus of a by 2 and minus of a by 2 and then minus of a by 2, and then I put r square. So, that is a square divided by 2, that is the second. What about the third? This is plus, and in the similar way I have 3 multiplication of plus chi 1. So, plus chi 1 means I should have chi 1 with negative value. So, a by 2, again I need to put minus a by 2 here in place of x minus a by 2 in place of x, and then minus of r square, which is same, which is a square divided by 2, because mod of all the values is same, that is equal to mod of 2 square. And finally, we have minus of 3 is here, and chi 2 is simply a by 2, a by 2, and then minus a square by 2. So, all the 4 value I calculated, and now what I get, let us see that that I am getting here, let us take 3 outside, 3q divided by 2, and then I get here a term a square divided by 4 minus a square divided by 2. So, it should be minus of a square divided by 2. These term I am having the same thing, but minus sign. So, I should have plus of a square divided by 2. This term is plus, so I should have minus of a square divided by 2, and this term again I have so this is 2. So, sorry, so it is a square, not a square by 2, I should have a square by 4 here, all the cases. So, this is 4, this is 4, this is 4, and I should have plus a square by 4. So, after doing all this calculation, we find that it is seems to be cancelling, and I am having 0. So, what I get is q 11 is 0. In the similar way, you will find q 22 is equal to 0. Now, I know q 11 plus q 22 plus q 33 has to be 0. Since this is 0 and this is 0, this has to be 0. So, that means q 33 is also 0. So, all the diagonal term will be 0. After doing all calculation, we figure out. So, the next thing that I am going to calculate is q 12. The calculation is seems to be a lengthy, but once you do this calculation by your own, then you are confident enough that how to calculate the quadrupole moment tensor. In the exam, this is nowadays this is a very popular question to calculate the quadrupole moment for a given charge distribution. Like so, for 1 2 I have an advantage. The advantage is if I write down, because a delta function is there. So, I can simply have, okay, let me write it first, 3 x 1 x 2 dash dash minus r prime square, and I should write delta 1 2, and then rho r prime dv prime. You can see that this quantity is 0. So, eventually I am having only these terms. So, r square term is no longer. For all the all the off diagonal terms, it is true. So, I simply have rho is known. So, I simply have q divided by 2, and then I have the integration over volume, and I have 3 x 1 prime x 2 prime, and the delta function, whatever the delta function is there. So, let me write it once again, delta once you do one problem, the rest of the thing is now just a repetition of the same thing. Plus delta one value you will get r prime minus, you know, no, let me follow the order otherwise. So here I should write minus of these things and it is plus, and we have plus delta r prime plus chi 1, and then I have a minus delta r prime and minus chi 2. Then this is dv, not delta. This is dv prime. Okay, so now again I need to just put the value, and if I put this value I should get 3q divided by 2 here, and let us start putting the value. So I first, when I put this one, so the value is a by 2 and a by 2, this is my first value. Second value with a negative sign I should put it, but it is 1 2, mind it, 1 2 means it is x y, right, it is x y. So let me write it because this is important. So chi 1 was a by 2 x plus a by 2 y, and chi 2 was a by 2 x minus a by 2 y. So that component, that x and y value is important here. So for chi 1 I have x value a by 2, y value a by 2, I put it. For minus of chi 2 I should have the x value as minus of a by 2 and the y value is plus of a by 2 because it is minus chi 2, and then I have plus minus of chi 1. For minus of chi 1 I have x and y both are minus of a by 2 and minus of a by 2, and finally for chi 2 I have value x a by 2 for x and minus of a by 2 for y. Okay, so let us see. So a by 2, so all the cases it is a by 2, so I can simply take 3q divided by 2 and this a square divided by 4 outside. Then what I am getting is 1 plus 1, then plus 1 plus 1. So that value is non-zero, mind it, that value is non-zero, and what I am getting is 4. So 3q divided by 2 a square, that is the value I am getting. So this is the value of q12. Okay. Now once you know q12, then you know that this is equal to q21, right. And now if I calculate q31 or q31 or q31 or q13, or q32 or q23, everything will be 0, Why? Because there is, for this is two dimensional, there is no z component sitting here, right. Since there is no z component, so I will going to get all whenever I have x3 here in this picture, these things will be 0 for all the cases. So, all this quantity should be 0 because in our case x3 prime is 0. I mean there should not be any x, I should not have, because this is in plane, no z component. So, so I have already figured out almost all the values, and also 2, 3, 3, 2, all these things are 0. So, 1, 2, 3, 4, 5, 6 and other 3, 7, 8, 9. So, all the 9 components are there. So, if I put these 9 components together, I will have q is equal to q 1 1, q 1 2, q 1 3, q 2 1, q 2 2, q 2 3, q 3 1, q 3 2, q 3 3, and the value should be this. This is seems to be 3 by 2 q a square, and I should have 0, this value is 1, this is 0, this value is 1, this is 0, 0, 0, 0, 0. This is the value of the quadrupole moment of this system. Now, the third part is what is the what is the value of the potential. That was the third problem. So, let me do it here as well. So, phi 3, that is the potential contribution of the quadrupole. For discrete case, it is 1 by 4 pi epsilon 0, then sum over I and j, this is xi xj whole divided by r to the power 5 and qij. So, that quantity qij I already figure out. So, that value if I put here, it should be epsilon 0 1 by 2 r to the power 5, and this okay. So, q okay, this not 2 here. So, I just need to put the qij. So, what qij get here? So, it is 1 2. So, it is x 1 x 2, because this is meaningful, all the value are 0, other value are 0, 1 2 plus x 2 1 q 2 1, because only x 1 2 and 2 1 is non vanishing, other all the values are 0. Now, if I put this, it simply comes out to be q a square divided by 4 pi epsilon 0 1 by r to the power of 5 and 3 x 1 x 2. This is the value. So, x 1 x 2 means it should be x and y. In terms of x 1 y, it should be q a square divided by 4 pi epsilon 0 r to the power 5 and then 3 x y. This should be the value. Okay, another 2 term should be here because it is 3 by 2. So, I should put a 2 here and another 2 should be here. So, this should be the potential due to this structure. Okay, so we are almost finishing our time, but quickly I like to show another thing, and that is for single charge system what happened. So, for single charge system, so let us first calculate that thing that I. So, if we mention that the dipole moment is independent of the choice of the origin, if total charge q is equal to 0. In the dipole moment, if the total charge q is equal to 0, then it is independent of the choice of the origin. So, we can prove it very quickly. So, suppose I have a coordinate system like this and a point here, charge distribution is here, and whose location with this coordinate system is r prime. So, according to my definition, it should be r prime, rho at r prime and dv prime. Now, what I do that I am going to shift this coordinate system to some other point, say here I shift it such that this is the origin. Now, I have a new origin here which is shifted by a quantity vector A, and from this new origin the point, the location of the with this new origin, the location is say now r prime A. Okay. So, for r prime A, for this origin, for this coordinate system, according to my definition, the dipole moment should be written as P A is equal to integration of, in place of r prime I should now write r A prime, because this is the location with this new coordinate, and then rho r prime A dv prime. This is the new value with new coordinates. Now, you can see that r prime is this quantity, and so r prime, okay, this is not r 1, r prime is simply r prime A minus vector A. So, if I put that and try to understand the relation between these two dipole moments. So, P is equal to integration of r prime rho r prime dv prime. Now, I am going to put the value. So, this is r prime A minus A and rho r prime A minus A and dv prime. So, this quantity is integration of this quantity is integration of r prime A and then rho r prime A minus A dv prime and minus A integration of rho r prime A minus A dv prime. Okay. So, this quantity is simply represented this because this is even if I put this. Okay, so let me write it here. This is simply A rho and r prime minus A, whatever the value of the density I will have, the same amount of density I should have for R A, because both the cases it is showing the same point, and minus A, this quantity is a total charge, right. Rho, this quantity dV prime is my total charge A into Q. So, this quantity is my P, is this my P A under new coordinate minus A of Q. So, there is a relationship between the dipole moment when we have, I should have a vector here, when we have a shift of the coordinate system. This is for old coordinate system and this is for new coordinate system. Now, you can see that it will be independent of the coordinate system if this quantity is 0. So, that means if the total charge distribution or the total charge in the distribution, if the total charge Q is equal to 0, that means the total charge is 0, we simply have P is equal to P A. So, whatever the dipole moment we have in the previous case, I can have the same. So, we can say that under the condition that when the total charge is 0, the dipole moment is a conserved quantity. So, dipole moment will depend on the coordinate system only if the total charge is non-zero. If the total charge is 0, then it is independent of the choice of the coordinate system. So, dipole so that is why when we have, if you remember, when we have two dipole plus and minus with plus q and minus q, this is the simplest example of a dipole, then the total charge q was 0 and we find that the dipole moment, whatever the coordinate system you use, will remain same. On the other hand, if you have a 3 charge system, say this is plus q, this is minus q and this is again plus q, and if somebody asks what should be the dipole moment of this system, then the total charge q is not equal to 0 here, and we did it one problem actually in the last class, and we checked that it entirely depends on that how the it depends on the coordinate system. It even though the charge is same, but because of the distribution it is different, that means the choice of coordinate system matters. So, for this case, when there is total charge 0, I should have the dipole moment should not have any preference over the coordinate system, but here we should have a preference when it is non-zero. So, with this note, I think I should stop here because my time is limited. So, in the next class we will start a new topic related to the potential equipotential surface, and conductor and dielectric will be covered in that part. So, thank you very much for your attention and see you in the next class.